How do you measure something that might not have edges? It's a strange question to ask in the dark, lying here with your thoughts still spinning from the day. But tonight, that's where we're going. Into the problem of size itself, into the question of whether the universe even has a boundary to find, and what it means when the thing you're trying to understand keeps growing faster than you can look. You've probably heard numbers before, billions of light years, trillions of galaxies, but numbers stop meaning much after a while. They become sounds without shape. So tonight, we're going to walk through this differently, slowly, with room to breathe between the ideas. We're going to ask, how big is the universe, really? And more importantly, how do we even begin to answer that? Welcome back, traveler. Tonight we drift through science. You're lying in bed right now, maybe with the faint glow of your screen the only light in the room, or perhaps you've already dimmed everything and you're just listening in the dark. The house is quiet. The world outside has slowed, and you're here because something about the bigness of everything feels like the right kind of company tonight. If this is the kind of science that helps you feel less alone in the immensity of it all, go ahead and leave a like. It tells me you want more nights like this. And if you feel like it, drop a comment telling me where you're listening from and what time it is where you are. There's something strangely comforting about knowing we're all scattered across the planet, lying in our own small rooms, looking up at the same enormous sky. Maybe you're here because sleep won't come. Maybe your mind is still looping through tomorrow's worries, or last week's conversations, or that thing you can't fix yet. That's okay. You don't need to fix anything right now. You don't need to be productive, or sharp, or even fully awake. You're allowed to be tired. You're allowed to let your mind wander while I talk, to miss entire sentences, to drift in and out. You don't have to remember the names of telescopes or the distances to faraway galaxies. You don't have to understand every detail to rest here. This isn't a test. It's just a voice in the dark, walking you through something bigger than both of us, at a pace that doesn't demand anything from you. Here on Orbis Sleep, we do something specific. This channel is for people who love big questions, but need a calm place to explore them at night. We take the universe seriously, the real science, the actual missions, the numbers that took decades to measure. But we also take you seriously. We know you're not here for a lecture. You're here because the cosmos feels like good company when the rest of the world is too loud or too close. So tonight, we'll move between two worlds. The one out there where galaxies stretch beyond comprehension and light takes billions of years to arrive, and the one down here where humans built machines and launched them into the void just to see a little farther. We'll talk about what we've found, yes, but also about how we found it. The telescopes that broke and got fixed, the data that looked like noise until someone realized it wasn't, the people in labs and control rooms who spent their lives trying to see past the edge of the visible. That's part of the story too, because the universe isn't just out there. It's also in the effort to understand it. Tonight, we'll walk slowly through the problem of cosmic size, and we'll do it without rushing. We'll start with what we can see, then move into what we can infer, and finally into what we might never know. Along the way, you'll float above galaxies, stand at the edge of observable space, and sit in the rooms where scientists first realized the universe was stranger and bigger than anyone had guessed. You'll hear about the machines we've sent out to measure it, and the strange, humbling failures that taught us how to look better. There's no finish line here, no final answer I'm building toward, just the journey itself, and the quiet realization that even asking the question changes how you see the night sky. So go ahead, turn off the light if you haven't already. Adjust your pillow, let your body settle. Close your eyes if you want, or keep them open and stare at nothing in particular. We're not in a hurry. The universe has been here for 13 billion years. It can wait while you get comfortable. You're floating in darkness, but it's not empty. If you could zoom out from your bed, past your ceiling, past the atmosphere, past the moon's quiet orbit, you'd see Earth glowing softly against the black, a blue marble held in nothing, turning slowly beneath a blanket of air so thin it barely registers as a layer at all. From up here, the planet looks small, but not impossibly so. You can still hold the whole thing in your mind. You can imagine walking its curve, flying over its oceans, touching its mountains. It has edges. It has a size you can grasp. And that's where the measurement problem begins, because the universe doesn't give you that courtesy. It doesn't fit in your hand or your mind or even in the largest number you've ever tried to picture. For most of human history, we thought the sky was a dome, not metaphorically, literally. The stars were fixed lights on a ceiling, and the ceiling had a distance. You could imagine reaching it if you climbed high enough, or flew far enough, or built a tower tall enough. That model made sense because it gave the cosmos a container. It gave it edges, and edges mean size. But then we started measuring things, and the dome cracked. First, we realized the stars weren't all the same distance away. Then we realized they weren't fixed at all. They were moving, some toward us, and some away. And then, in the early 20th century, we realized something that broke the model entirely. The stars weren't even the biggest thing. They were inside galaxies, and the galaxies were moving too. The man who cracked it open was named Edwin Hubble, and he worked at the Mount Wilson Observatory in California in the 1920s, using a telescope that was, at the time, the largest in the world. He was looking at faint smudges of light that astronomers had been arguing about for years. Some thought they were clouds of gas inside our own galaxy. Others thought they might be separate galaxies altogether. Hubble found a type of star inside one of those smudges, a Cepheid variable, a star that pulses in brightness at a predictable rate. And because we knew how Cepheids worked, Hubble could measure how far away it was. The answer was staggering. The smudge wasn't inside the Milky Way. It was almost 1 million light-years away. It was another galaxy entirely. The universe had just gotten 1,000 times bigger in a single observation. But Hubble didn't stop there. He kept measuring distances to other galaxies, and he noticed something strange. The farther away a galaxy was, the faster it seemed to be moving away from us. Not just drifting, fleeing, and not just from us. Every galaxy was moving away from every other galaxy, as if space itself was expanding. This wasn't an explosion outward from a center. It was everything stretching at once, like dots drawn on the surface of a balloon that's being inflated. You're still lying in your bed, but the room you're in is sitting on a planet that's orbiting a star that's inside a galaxy that's hurtling through expanding space at over 1 million miles per hour. You've always been moving. You just never felt it. That discovery changed the question. It wasn't just how big is the universe as anymore. It was how fast is it growing, and was there a time when it wasn't big at all? The answers pointed backward, toward a moment roughly 13.8 billion years ago, when everything we can see, every galaxy, every star, every atom, was compressed into a space smaller than a single point. We call it the Big Bang, though that name makes it sound like an explosion in empty space, which it wasn't. There was no space yet. There was no outside. The Big Bang was the beginning of space itself, and time, and everything that would eventually become you lying here in the dark, listening to this. Here's the first hard number to anchor yourself to. The observable universe, the part we can actually see, is about 93 billion light-years across. That's the diameter, not the radius, the full width. If you wanted to travel from one edge to the other at the speed of light, it would take you 93 billion years, which is longer than the universe has existed. And that's the first strange thing. The universe is older than 13.8 billion years, But the observable part is bigger than 13.8 billion light-years across. That seems impossible. How did light from distant galaxies travel farther than the age of the universe would allow? The answer is expansion. While light was traveling toward us, space itself was stretching, carrying those galaxies farther away even as their light crawled closer. So by the time the light reaches us, the galaxy that emitted it is now much farther than it was when the light began its journey. You don't have to hold all of that in your head at once. Just picture this. Every photon of light that hits your eye tonight has been traveling for a long time. Maybe a few minutes if it came from the sun. Maybe a few years if it came from a nearby star. Maybe billions of years if it came from a distant galaxy. And the farther back in time you look, the younger the universe appears. When you look at a galaxy 10 billion light-years away, you're not seeing it as it is now. You're seeing it as it was 10 billion years ago, when the universe was still a childless, when stars were being born in massive bursts, when galaxies were smaller and closer together and colliding more often. The sky is a time machine. The deeper you look, the farther back you go. This is where the telescopes come in, the human experiments, the machines we built to see farther than our eyes allow. Hubble's telescope was made of glass and metal, mounted on a hillside under the California sky. But in 1990, we launched a telescope into space, above the atmosphere, where there's no air to blur the light. We named it after Edwin Hubble. The Hubble Space Telescope orbits Earth every 97 minutes, staring into deep space, collecting photons that have traveled for billions of years. It's been up there for over 3 decades now, and it's shown us galaxies that formed less than 1 billion years after the Big Bang, places so distant that their light has been stretched by the expansion of space, shifting from visible colors into the infrared. But even Hubble has limits. It can only see so far, only capture so much light. So in 2021 we launched something bigger, the James Webb Space Telescope, a machine with a mirror 21 feet across, folded up like origami and sent 1 million miles from Earth to a gravitationally stable point in space where it can stare into the universe without interruption. Webb sees in infrared, which means it can look through the dust clouds that block visible light, and it can see galaxies that are even older, even farther, even stranger. Some of the galaxies Webb has photographed formed just a few 100 million years after the Big Bang, so early that they shouldn't exist yet according to our models. But there they are, shining back at us, forcing us to rewrite what we thought we knew. There's something humbling about that. We build these machines with the best physics we have, launch them into space, and then they send back images that break our theories. It's not a failure. It's how science works. You make a model, you test it, and the universe tells you where you were wrong. The people at NASA and ESA and other space agencies spend years preparing for these missions, checking every sensor, every line of code, every alignment, and still, things go wrong. Webb's mirror had to unfold perfectly in space, a process with over 300 potential points of failure. And it worked. But Hubble, back in 1990, launched with a mirror that had been ground incorrectly by a fraction of a wavelength. The images came back blurry. It took 3 years and a spacewalk repair mission to fix it, and even then it became one of the most successful scientific instruments ever built. You're still lying here while all of this unfolds above you. Machines orbiting in silence, galaxies shining across billions of years, light crawling through the expanding void. You don't have to visualize all of it. You don't have to remember the names or the numbers. Just know that the question, how big is the universe, has been answered in layers, each one stranger than the last. First, we measured the Earth, then the solar system, then the galaxy, then the distance to other galaxies. And then we realize that distance itself is unstable, that space is stretching, that the universe is not a static stage but a living, expanding thing. And we're inside it, trying to measure it from the inside. Like an ant trying to understand the size of the planet by walking across a single leaf. The observable universe is not the whole universe. That's the next piece to hold gently in your mind. What we can see is limited by the speed of light and the age of the universe. There are galaxies out there whose light hasn't reached us yet, and there are galaxies whose light never will reach us, because space is expanding faster than light can cross it. Those galaxies exist, but they are beyond the horizon of observation. They are real but invisible, unreachable. And that means when we say the universe is 93 billion light years across, we're only talking about our little bubble of visibility. Beyond that, we don't know. It could go on forever, it could loop back on itself, it could be infinite, or it could have an edge we'll never see. Here's a metaphor to carry with you. Imagine you're standing in the middle of a foggy field at night. You have a flashlight, and the beam reaches 100 feet in every direction. That's your observable universe. You can see grass, maybe a few trees, the outline of a hill. But beyond the edge of the light, the field keeps going. You just don't know how far. Maybe it ends at a fence a mile away. Maybe it stretches to the horizon. Maybe it never ends at all. The fog doesn't stop existing just because you can't see through it. And the universe doesn't stop existing just because its light hasn't reached you yet. You're standing in the middle of something vast, holding a small light. And the size of the field is not the size of the light. It's bigger, maybe much bigger, maybe infinitely bigger. And that's where we'll pause for now. You've drifted from your bed to the edge of the observable universe, from the first measurements of galaxies to the realization that space itself is expanding, carrying everything away from everything else. You've learned that the sky is a time machine, that telescopes are our way of looking backward, and that the universe we can see is only a piece of the universe that exists. You don't need to solve it tonight. You don't need to hold the whole thing in your mind. Just breathe. Let the ideas settle like dust. You're still here, still safe, still lying in the dark. And the universe, vast as it is still out there, waiting patiently while you rest. You're awake again, or maybe you never fully drifted off. That's fine. There's no schedule here, no place you need to be. We left off standing at the edge of what we can see, 93 billion light years across. A bubble of visibility carved out by the speed of light and the age of time itself. But now we need to ask a harder question. If that's just what we can observe, what lies beyond it? And more unsettling still, how do we talk about the size of something when we can't see its edges, when the very act of looking changes what we're measuring, when the thing we're trying to understand is expanding faster than we can chase it? Let's start with something simpler. Imagine you're holding a balloon that hasn't been inflated yet. You draw 2 dots on its surface with a marker, close together. Then you start blowing air into the balloon. As it expands, the dots move apart, not because they're traveling across the surface, but because the surface itself is stretching. They're not moving through space. Space is moving them. That's what's happening with galaxies. They're not flying away from us through some pre-existing void. The void itself is growing, and they're being carried along with it. Edwin Hubble saw this in the 1920s, but he didn't have the full picture yet. He saw the motion, but he didn't know why. That answer came later, from a different kind of experiment, one that involved mathematics, not telescopes. In 1915, Albert Einstein published his theory of general relativity, a new way of understanding gravity. He said that mass and energy bend the fabric of space and time, creating curves that objects follow. A planet doesn't orbit a star because of some invisible force pulling on it. It orbits because the star warps space around it. and the planet is simply moving along the straightest possible path through that warped space. It's like rolling a marble on a stretched rubber sheet with a bowling ball in the middle. The marble spirals inward, not because the bowling ball is pulling it, but because the sheet is curved. Einstein's equations described how matter shapes space and how space tells matter how to move. But when he applied those equations to the universe as a whole, he found something troubling. The math said the universe couldn't be static. If space contained matter, it had to be either expanding or contracting. It couldn't just sit still. Einstein didn't like that. He believed the universe was eternal and unchanging, so he added a term to his equations, something called the cosmological constant, to hold everything in place, to keep the universe from collapsing or growing. It was a fudge factor, a mathematical trick to make the equations match his intuition. But then Hubble published his observations showing that galaxies were moving apart, and Einstein realized his mistake. He later called the cosmological constant his greatest blunder. He'd had the answer in his hands, the universe was expanding, and he dismissed it because it didn't fit his expectations. But here's the strange part. The cosmological constant came back. Decades later, in the 1990s, astronomers were measuring distant supernovae, exploding stars that shine with a predictable brightness, making them useful as cosmic distance markers. They wanted to know how much the expansion of the universe was slowing down over time. Gravity should be pulling everything back together, right? So the expansion should be decelerating. But when they ran the numbers, they found the opposite. The expansion wasn't slowing, it was speeding up. Galaxies weren't just drifting apart, they were accelerating away from each other, pushed by something invisible, something we now call dark energy. And the math that describes it looks almost exactly like Einstein's cosmological constant. He was right by accident. The universe does have a strange outward pressure built into the fabric of space itself. You're lying in your bed on a planet that's orbiting a star that's inside a galaxy that's being pushed away from every other galaxy by a force we don't understand. Dark energy makes up about 68% of the universe's total energy content. But we don't know what it is. We just know it's there because we can see its effects. It's like watching leaves scatter across a sidewalk and knowing the wind is blowing, even if you can't see or touch the wind itself. We've named it. We've measured its strength, but we haven't explained it. And that means when we ask, how big is the universe, we're also asking how fast is dark energy pushing it apart, and will it ever stop? And what happens when galaxies move so far away that their light can never reach us anymore? Here's another number to hold lightly. The universe is expanding at about 70 kilometers per second per megaparsec. That's the Hubble constant. Though we now know it's not actually constant, it changes over time as the universe evolves. But what does that number mean? It means that for every megaparsec of distance, about 3.3 million light years, space is stretching by 70 kilometers every second. So a galaxy that's 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. And once you get far enough out, galaxies are moving away faster than the speed of light. Not because they're traveling through space that fast, but because space itself is expanding that fast. They're being carried by the current. This is where things start to bend your intuition. You've probably heard that nothing can move faster than light. That's true. Nothing can move through space faster than light. But space itself isn't bound by that rule. Space can stretch as fast as it wants, and that means there's a boundary out there, a distance beyond which galaxies are receding so quickly that their light will never reach us no matter how long we wait. We call it the cosmic event horizon. It's not a physical barrier. You couldn't fly to it and touch it. It's just a line in space beyond which information can't cross. Galaxies beyond that line exist, but they're invisible to us forever. They're on the other side of an unbridgeable gap, not because they're too far, but because the space between us and them is growing faster than light can close it. The scientists who discovered the acceleration of the universe didn't expect it. They were measuring supernovae using telescopes on the ground and in space. Hubble, Keck Observatory in Hawaii, Cerro Tololo in Chile. They spent years collecting data, checking their instruments, ruling out errors. One team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. Another was led by Brian Schmidt and Adam Rees, working with telescopes scattered across the globe. Both teams thought they were racing to measure the deceleration of the universe. Instead, they both found acceleration. At first, they thought something was wrong with their data. They checked for dust, for calibration errors, for mistakes in the code. But the result held. In 1998, they published their findings. The universe wasn't slowing down. It was speeding up. And in 2011, Perlmutter, Schmidt, and Rees won the Nobel Prize for discovering something no one had predicted. You don't have to picture all of this. Just feel it. You're resting in a universe that's not resting. It's stretching, accelerating, carrying galaxies away from each other like debris in a river that's flowing faster and faster towards some unknown destination. And because the expansion is accelerating, the observable universe, the bubble of space we can see, will eventually stop growing. New light will stop reaching us. Distant galaxies will fade from view, red-shifted into invisibility. And one day, billions of years from now, an astronomer in a far future civilization will look up at the sky and see only the stars in their own galaxy. The rest of the universe will have slipped beyond the horizon. They'll have no way of knowing it was ever there. But we're not there yet. Right now, tonight, while you're lying here, we can still see 13.8 billion years into the past. We can still map the structure of the universe, trace the web of galaxies, measure the distribution of matter and energy. And one of the strangest things we've discovered is that the universe isn't uniform. It's not a smooth soup of galaxies scattered randomly. It's more like a foam or a web. Galaxies cluster together along vast filaments of dark matter, separated by enormous voids where almost nothing exists. These structures are hundreds of millions of light years across, and they formed over billions of years as gravity pulled matter together, slowly, patiently, building the cosmic architecture we see today. Dark matter is another invisible player in this story. We can't see it directly. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. But we know it's there because we can see its gravity at work. Galaxies spin too fast for the amount of visible matter they contain. Galaxy clusters hold together with more gravitational pull than their stars and gas can account for. And when we map the large-scale structure of the universe, the patterns only make sense if there's about 5 times more dark matter than ordinary matter. We don't know what it is. We've built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with an atomic nucleus. So far, nothing. But the search continues, in labs in Italy, in China, in abandoned mines in South Dakota, in detectors floating beneath Antarctic ice. Here's the picture forming. The universe is mostly made of things we can't see. 68% dark energy, 27% dark matter, and only 5% ordinary matter, the stuff that makes up stars, planets, people, everything you've ever touched or seen. We're the minority, we're the exception, and yet we're the part that's trying to measure the whole. It's like trying to understand an ocean by studying the foam on a single wave. We're doing our best with what we have. We've built machines that can see across billions of light years. We've measured the expansion rate, the age of the universe, the distribution of galaxies. We've mapped the cosmic microwave background, the faint afterglow of the Big Bang itself, still shining in every direction. A kind of baby picture of the universe taken when it was only 380,000 years old. That's another human experiment worth mentioning. In the 1960s, two scientists named Arno Penzias and Robert Wilson were working with a radio antenna at Bell Labs in New Jersey, trying to detect faint radio signals bouncing off satellites. But they kept picking up noise, a persistent hiss coming from every direction in the sky at a very specific frequency. They thought something was wrong with the antenna. They cleaned out pigeon droppings. They checked for electrical interference. The noise didn't go away. Eventually, they realized they'd stumbled onto something enormous, the cosmic microwave background, the leftover radiation from the Big Bang, cooled and stretched by the expansion of space into microwaves. It was the echo of the beginning still reverberating through the universe. Penzias and Wilson won the Nobel Prize for it, though they'd been trying to get rid of it at first. You're still here, still breathing, still lying in the same spot you started. But now you're holding a different picture. A universe made mostly of invisible things, expanding faster and faster, carried by a force we don't understand, filled with galaxies arranged in vast structures that took billions of years to form. And somewhere in the middle of all that, there's you, made of ordinary matter, temporary, small, but aware. Aware enough to ask how big it all is, aware enough to build telescopes and launch them into space, aware enough to lie awake at night and wonder. You don't need to solve the mystery. You're part of it. That's enough for now. Just rest. Let the immensity sit beside you like a quiet companion. It's been here all along. You're still floating in the dark, but now we're going to pull back even further. Past the galaxies, past the cosmic web, past the edge of what we can see with our best telescopes. We're going to ask a question that sounds simple but cuts deeper than almost anything else in cosmology. Does the universe have a shape? Not just a size, but a geometry. Is it flat like an infinite sheet of paper, or curved like the surface of a sphere, or bent in some other way we can't easily visualize? The answer matters because shape determines fate. It tells us whether the universe will expand forever, whether it might one day collapse back on itself, whether space is finite or infinite. And the strange thing is, we can measure this. We can test the shape of the universe by looking at light. The tool we use is the cosmic microwave background, that faint radiation left over from the Big Bang, the echo we talked about earlier. When the universe was only 380,000 years old, it was hot and dense, filled with plasma so thick that light couldn't travel freely. But as it expanded and cooled, the plasma thinned, and light finally broke free, streaming out in every direction. That light has been traveling ever since, and it's now stretched into microwaves by the expansion of space. We can see it everywhere we look, a faint glow at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. And embedded in that glow are tiny fluctuations, hot spots and cold spots, imprinted when the universe was still a baby. Those fluctuations tell us about the density of matter back then, and they also tell us about the geometry of space itself. Here's how it works. Imagine you're looking at ripples on the surface of a pond. If the pond is flat, the ripples spread out in perfect circles. But if the pond is curved, say wrapped around a sphere, the ripples would look distorted, stretched or compressed depending on the curvature. The same thing happens with light in the universe. If space is flat, light travels in straight lines, and the patterns in the cosmic microwave background appear at a certain angular size. If space is positively curved, like the surface of a sphere, the patterns look bigger than expected. If it's negatively curved, like a saddle, they look smaller. We've measured those patterns with incredible precision, using satellites like WMAP and Planck, and the answer is startling. The universe is flat, or so close to flat that we can't measure any curvature. The margin of error is less than 0.5%. But flat doesn't mean finite. That's the confusing part. A flat universe could go on forever, infinite in every direction. Or it could loop back on itself in strange topological ways, like a three-dimensional version of the old video game, where you fly off one edge of the screen and reappear on the other. We don't know which. The observable universe is flat within our bubble of visibility, but we can't see far enough to know if it curves somewhere beyond the horizon, or if it twists into some configuration we haven't imagined yet. All we can say is that if you drew a triangle with sides billions of light years long, the angles would add up to exactly 180 degrees, just like they do on a flat piece of paper. Space, at least the part we can measure, doesn't bend. The people who figured this out spent years staring at maps of the sky. The Planck satellite, launched by the European Space Agency in 2009, orbited a point in space called L2, about 1 million miles from Earth, on the opposite side from the Sun, where it could scan the entire sky without interference from the Earth or the Moon. It measured temperature fluctuations in the cosmic microwave background down to millionths of a degree, pixel by pixel, building a map of the infant universe. The data had to be cleaned carefully, removing noise from the instruments, subtracting the glow of our own galaxy, filtering out radiation from distant galaxies. What remained was a mottled pattern, red and blue blotches across the sky, showing where the universe was slightly hotter or cooler 14 billion years ago. From those blotches, cosmologists extracted the shape of space, the age of the universe, the ratio of dark matter to dark energy, and a dozen other fundamental parameters. It's one of the most precise measurements in all of science, and it was done by pointing a telescope at nothing and listening to the hum of creation. So the universe is flat, but that creates a new problem. In the early 1980s, a physicist named Alan Guth realized that the standard Big Bang model had some serious issues. One of them was the flatness problem. If the universe started out even slightly curved, the expansion would have amplified that curvature over time. A universe that was almost flat in the beginning should be wildly curved now, but it's not. It's still flat. That means the early universe must have been fine-tuned to an absurd degree, flat to within 1 part in 10 to the 60th power. That's not impossible, but it's deeply suspicious. It's like balancing a pencil on its tip and having it stay there for billions of years. Something else must be going on. Guth's answer was inflation, a brief, violent expansion in the first fraction of a second after the Big Bang, during which the universe grew exponentially, doubling in size over and over again in a time span shorter than you can imagine. In less than a trillionth of a trillionth of a trillionth of a second, the universe expanded by a factor of at least 10 to the 26th power, smoothing out any curvature, stretching space so flat that it looks flat even now, billions of years later. Inflation also explains why the universe looks the same in every direction. It was all in close contact before inflation, so it had time to reach the same temperature. And then inflation blew it apart so fast that different regions couldn't communicate anymore. They've been isolated ever since, but they still carry the memory of that early uniformity. Inflation is still a hypothesis, not a confirmed theory. We have strong indirect evidence, the flatness of space, The uniformity of the cosmic microwave background, the patterns of fluctuations that match what inflation predicts, but we haven't seen direct proof. Scientists are searching for it in the polarization of the cosmic microwave background, looking for a specific signature called B modes that would be left by gravitational waves rippling through space during inflation. Several experiments are underway. Telescopes at the South Pole, observatories in the Atacama Desert in Chile, balloon-borne instruments launched into the stratosphere. In 2014, a team thought they'd found it, announced the discovery, and then had to retract it when they realized the signal was contaminated by dust in our own galaxy. The search continues. Inflation fits the data beautifully, but science doesn't reward beautiful ideas unless they're proven. Here's the unsettling thought. If inflation happened once, it might still be happening elsewhere. Some versions of the theory suggest that inflation never fully stops. It ends in some regions, creating pockets like our universe, but continues in others, spawning new universes in an endless process. This is called eternal inflation, and it leads to the idea of a multiverse, an infinite collection of bubble universes, each with its own laws of physics, its own constants, its own history. Our universe would just be one bubble in an infinite foam, forever out of contact with the others. We could never see them, never visit them, never confirm they exist. It's a possibility that sits at the edge of science and philosophy, untestable but mathematically consistent. Some physicists love it, others hate it. It doesn't change the fact that our universe is still here, still flat, still expanding. You don't have to decide what you believe. You're just listening, floating through ideas like clouds drifting past a window. The universe is flat, at least the part we can see. It might be infinite, or it might loop back on itself in ways we haven't detected. It might be one of countless universes, or it might be the only one. We've measured its shape with satellites and mathematics, traced its geometry in the faint glow of the Big Bang, and found that it obeys rules we can write down on paper. That's remarkable when you think about it. The universe didn't have to be comprehensible. It didn't have to follow math we could understand, but it does. And so we keep looking, keep measuring, keep asking questions that push at the edges of what's knowable. You're still here. The room is still dark, and the universe, flat and vast and strange, is still out there, holding its secrets gently. Rest. There's more to come, but not yet. Not yet. You're beginning to see the pattern now. Every time we answer one question about the universe, 3 more appear in its place. We've measured the size of the observable universe, traced its expansion, mapped its shape. But there's another layer beneath all of that. Something that determines not just how big the universe is, but whether it could have been any other way. We're talking about the constants, those fixed numbers woven into the fabric of reality, the values that dictate how particles interact, how gravity pulls, how light moves. And here's the uncomfortable truth. If any of those numbers were even slightly different, the universe as we know it couldn't exist. Stars wouldn't form, atoms wouldn't hold together. You wouldn't be here, lying in the dark, listening to this. Take the strength of gravity. It's described by a number called the gravitational constant, usually written as G. It's incredibly weak compared to the other forces in nature, weak enough that you can lift a piece of paper off a table, overcoming the gravitational pull of the entire Earth with just your fingers. But if gravity were even a tiny bit stronger, stars would burn too hot and too fast, exhausting their fuel in millions of years instead of billions. Planets wouldn't have time to form, life wouldn't have time to evolve. If gravity were a tiny bit weaker, stars wouldn't ignite at all. Matter would drift through space in cold clouds, never collapsing, never fusing, never creating the heavy elements that make up your body. The fact that gravity is exactly the strength it is, not a little more, not a little less, is one of the reasons you exist. Then there's the strong nuclear force, the glue that holds atomic nuclei together. Protons have positive charge, and they repel each other. Without the strong force, they'd fly apart, and atoms heavier than hydrogen couldn't exist. But the strong force is perfectly calibrated, strong enough to bind protons and neutrons into stable nuclei, but not so strong that it locks them into combinations that wouldn't allow chemistry. If it were 5% stronger, almost all hydrogen in the early universe would have fused into helium, and there'd be no hydrogen left for water, for organic molecules, for stars like the Sun. If it were 5% weaker, deuterium, a key step in stellar fusion, wouldn't form and stars would never ignite. 5%. That's the margin. The universe sits on a knife's edge. The same thing applies to the fine structure constant, a dimensionless number that governs the strength of electromagnetic interactions. It's approximately 1 divided by 137, and no one knows why it has that value. Richard Feynman, one of the greatest physicists of the 20th century, called it one of the greatest damn mysteries of physics. If that number were much larger, atoms couldn't hold their electrons. If it were much smaller, chemical bonds wouldn't form the way they do, and the complex chemistry required for life would be impossible. We can measure it to extraordinary precision, 15 decimal places and counting, but we can't explain it. It's just there, embedded in the structure of reality like a signature we don't know how to read. Some scientists call this fine-tuning, and it makes them uncomfortable. It feels too convenient, too lucky. One response is the anthropic principle. Of course, the constants are right for life, because if they weren't, we wouldn't be here to notice. We're observing a universe that's compatible with our existence because incompatible universes don't produce observers. It's a selection effect, like a fish marveling at how perfectly suited water is for swimming. The fish only exists because water exists. If water didn't exist, there'd be no fish to wonder about it. But that answer doesn't satisfy everyone. It explains why we see what we see, but it doesn't explain why the constants have the values they do in the first place. Another response is the multiverse, the idea we touched on earlier. If inflation spawns countless bubble universes, each with randomly assigned constants, then most of those universes would be sterile, lifeless, structureless. But somewhere in that vast ensemble, a few bubbles would roll the dice and get values compatible with stars, planets, chemistry, life. We happen to live in one of those bubbles, not because it was designed for us, but because we couldn't exist anywhere else. The multiverse turns fine-tuning into a statistical inevitability, but it also makes the question untestable. If we can never observe other universes, never measure their constants, never visit them or communicate with them, then the multiverse isn't science, it's metaphysics. It might be true, but we can't prove it. There's a third option, quieter and less dramatic. Maybe the constants aren't random at all. Maybe there's a deeper theory waiting to be discovered, some underlying principle that explains why the numbers are what they are, that shows they couldn't have been any other way. String theory is one attempt at this, a framework that tries to unify all the forces and particles into a single mathematical structure. In string theory, particles aren't point-like objects but tiny vibrating strings, and the different ways they vibrate determine what kind of particle they are. The constants of nature in this picture emerge from the geometry of extra dimensions curled up at scales too small to see. But string theory has its own problems. It predicts a vast landscape of possible universes, maybe 10 to the 500th power different configurations, and we don't know which one we're in or why. It's mathematically beautiful, but it hasn't made a testable prediction yet. After decades of work, it remains a promising idea without experimental confirmation. The people working on these problems aren't philosophers sitting in armchairs. They're physicists running experiments, building particle accelerators, analyzing data from the Large Hadron Collider at CERN, searching for deviations from the standard model that might hint at deeper laws. They're cosmologists studying the cosmic microwave background, looking for signs that the constants have changed over time, testing whether the fine structure constant was slightly different in the early universe. So far, it looks stable, the same value now as it was billions of years ago. But the search continues, because if even one constant turned out to vary, it would crack open a door to new physics. It would mean that our constants aren't truly constant, and that would change everything. You're lying in a universe held together by numbers we didn't choose, governed by rules we discovered but didn't invent. The strength of gravity, the charge of the electron, the mass of the proton. These aren't arbitrary. They're measured, catalogued, tested to extraordinary precision, and yet we don't know why they are what they are. We don't know if they could have been different, or if they're locked into place by some principle we haven't found yet. We only know that they work, and that they work together in a way that allows stars to shine, atoms to bond, planets to form, life to emerge. It's not proof of purpose. It's not a guarantee of meaning. But it's strange enough to make you pause. Strange enough to make you wonder whether the universe is more carefully balanced than we give it credit for. Here's what you can hold on to. You're made of atoms forged in stars, held together by forces calibrated to a precision we're still trying to understand. The fact that you exist means the universe got the math right, at least once, at least here. You don't need to solve the mystery tonight. You don't need to know whether the constants were chosen or inevitable, or one random roll of an infinite number of dice. You're here. That's enough. The universe is vast, yes, but it's also surprisingly fragile, balanced on the edge of possibility. And somehow, against all odds, it produced you, lying in the dark, listening to the story of how it all fits together. Rest now. Let the numbers fade. You're part of the balance. That's all you need to know for now. You're halfway through the night now, halfway through the journey. We've traveled from the edge of the observable universe back to the constants that hold it together. And now we're going to ask a question that physicists have been wrestling with for decades. What happened before the Big Bang? It sounds like a simple question, but it might not even make sense. Time itself began with the Big Bang, or so the standard model tells us. There was no before because there was no time for anything to happen in. But that answer feels like a cheat, doesn't it? It feels like closing a door just when things were getting interesting. And so scientists keep pushing at it, searching for ways to peek behind the curtain, to understand what set the whole thing in motion. The Big Bang wasn't an explosion in space. It was an explosion of space. There was no center, no point where it happened. It happened everywhere at once because everywhere was compressed into a single point. At the very beginning, in the first fractions of a second, the universe was unimaginably hot and dense, temperatures so high that matter as we know it couldn't exist. Protons, neutrons, electrons, they hadn't formed yet. There were only elementary particles and energy, swirling in a kind of primordial soup. As the universe expanded and cooled, particles began to stick together. Quarks combined into protons and neutrons. Protons and neutrons fused into the first atomic nuclei, and after about 380,000 years, electrons finally settled into orbit around those nuclei, forming the first atoms. That's when the cosmic microwave background was born, the moment the universe became transparent, when light could finally travel freely. But what came before all that? What lit the match? One possibility is that the Big Bang wasn't the beginning at all, it was a transition. Some models suggest the universe went through a phase before the Big Bang, a kind of pre-existing state that collapsed or bounced or transformed into the hot, dense fireball we call the beginning. These are called cyclic models, and they imagine the universe as eternal, going through endless cycles of expansion and contraction, each Big Bang followed eventually by a big crunch, which triggers another Big Bang, and so on forever. In this picture, our universe is just one chapter in an infinite book, and the question of ultimate origins never gets answered. It just gets pushed back infinitely. Another idea is quantum cosmology, which tries to apply the strange rules of quantum mechanics to the universe as a whole. In quantum mechanics, particles don't have definite positions or velocities until you measure them. They exist in a haze of probabilities, a superposition of all possible states. What if the universe itself emerged from a quantum fluctuation, a random blip in the fabric of something? In this view, the Big Bang didn't need a cause in the traditional sense. It was a quantum event, probabilistic, spontaneous. The universe tunneled into existence out of nothing, or out of a pre-geometric state where time and space didn't yet have meaning. It sounds like science fiction, but the math is real, and physicists like Stephen Hawking spent years developing these models, trying to describe the birth of the universe without invoking anything outside of physics. Hawking's approach, developed with James Hartle in the 1980s, was called the no-boundary proposal. They imagined the early universe not as a singular point where time begins, but as a kind of smooth, closed surface, like the surface of a sphere, where time gradually emerges from a more fundamental timeless state. If you try to trace time backward toward the Big Bang, it doesn't hit a hard edge. Instead, it curves, blending with space in a way that makes the question, what came before? Meaningless, like asking what's north of the North Pole. There's no north of the North Pole. The direction just stops making sense. Hawking's model suggests that the same thing happens with time at the beginning of the universe. It's not that time started, it's that the concept of before dissolves into something else. These ideas are hard to test. We can't rewind the universe, can't observe the Big Bang directly, can't visit the quantum foam or the pre-Big Bang state, if such a thing even exists. But we can look for clues. One place to search is in the polarization of the cosmic microwave background, where gravitational waves from the earliest moments of the universe might have left a faint imprint. Another is in the distribution of galaxies and the large-scale structure of the cosmos, which carries information about the initial conditions. Physicists are also building detectors to search for primordial gravitational waves, ripples in space-time from the Big Bang itself, still echoing through the universe. LIGO and Virgo have detected gravitational waves from colliding black holes and neutron stars, but the waves from the Big Bang would be much older, much fainter, woven into the background noise of space. There's also the possibility that we're asking the wrong question. Maybe us before the Big Bang is a category error, like asking what color time is or how much a thought weighs. Our intuitions about causality, that every event needs a prior cause, come from living inside time, where cause always precedes effect. But if time itself is part of the universe, part of what came into being, then the rules might be different at the boundary. The universe might not need a cause in the way we normally think of causes. It might just be the way a circle just is, with no beginning or end, no point where it starts. That's unsatisfying to our storytelling minds, which crave origins and explanations. But the universe doesn't owe us a story that makes intuitive sense. Some scientists have tried to preserve causality by invoking something outside the universe, a multiverse, a higher dimensional space, a quantum vacuum seething with potential universes waiting to be born. Others have suggested that the laws of physics themselves might evolve, that what we think of as constants and rules might be more like habits the universe developed over time. These ideas live at the edge of science, where math and philosophy blur together, where models become speculative and experiments become impossible. It's not that the questions are unanswerable, it's that the answers might require tools we haven't invented yet, or concepts we haven't imagined. Here's what we do know. The universe had a beginning in the sense that it was once much smaller, much hotter, much denser than it is now. We can trace its history back to a fraction of a second after the Big Bang, and the story we tell, inflation, nucleosynthesis, the formation of atoms, the release of the cosmic microwave background, matches the evidence beautifully. But the very first moment, the actual instant of the bang, remains hidden behind a wall of ignorance. Our equations break down, our models fail. We hit a singularity, a point where density and temperature become infinite and the math stops working. That's usually a sign that we're missing something, that there's a deeper theory waiting to be found, maybe quantum gravity, maybe something else, that will smooth out the singularity and show us what really happened. You don't have to resolve it tonight. You're lying in a universe that might have had a beginning, or might be part of an eternal cycle, or might have tunneled into existence from a quantum void. It might have been caused by something we'll never see, or it might have been uncaused. A brute fact, the ultimate free lunch. The question is still open. The scientists are still working. And in the meantime, the universe is here, vast and old and full of mysteries, carrying you through the dark on a planet that orbits a star that was born from the ashes of earlier stars, in a galaxy that's part of a cosmic web that stretches back to the first moments after the beginning, whatever the beginning was. Rest. Let the uncertainty sit beside you like an old friend. Not everything needs an answer. Not tonight. You're drifting again, somewhere between thought and sleep, and that's exactly where we need to be for this next piece. We've talked about size, about expansion, about the shape and the constants and the beginning. But now we need to confront something more immediate, more personal. The fact that most of the universe is not just far away, it's disappearing. Not gone yet, but slipping beyond reach, carried away by the accelerating expansion we talked about earlier. Right now, tonight, while you're lying here, there are galaxies whose light is reaching us for the last time. Tomorrow, they'll be a little farther. Next year, farther still. And eventually, they'll cross a threshold where no signal they send, no light, no gravitational wave, no information of any kind, will ever reach us again. This is the cosmic event horizon, and it's not like the horizon you see at the ocean, where the Earth curves away and hides what's beyond. The cosmic horizon is a consequence of expansion. Space is stretching, and the farther away something is, the faster it's receding. At a certain distance, roughly 16 billion light-years from us right now, galaxies are moving away at exactly the speed of light. Beyond that line, they're receding faster than light, and any photon they emit in our direction will never close the gap. It's like trying to swim upstream in a river that's flowing faster than you can swim. You make progress relative to the water, but you're still being carried backward. The photon crawls toward us, but space is opening up between us faster than the photon can travel. What that means, practically, is that the observable universe is shrinking in terms of what's accessible. The bubble of space we can interact with is getting smaller over time. Even though the universe as a whole is getting bigger, it's a strange inversion. Galaxies aren't leaving the universe, they're leaving our universe, the portion we can observe and influence and ever hope to reach. In a few trillion years, if any civilizations still exist, if any astronomers are still looking up, they'll see a much lonelier sky. The distant galaxies will have faded into the infrared and then vanished entirely, their light redshifted into nothingness. Only the galaxies in our local group, bound together by gravity, close enough that expansion can't tear them apart, will remain visible. There's something melancholy about that. The universe isn't just vast, it's slipping away. We're living in a brief window of time when the cosmos is still visible, when we can still see the afterglow of the Big Bang, still map the large-scale structure, still trace the history of the universe back to its infancy. In the deep future, that won't be possible. Future astronomers will look out and see only a handful of nearby galaxies, all slowly merging into one giant elliptical galaxy. They'll have no evidence of the Big Bang, no cosmic microwave background to study, no distant supernovae to measure. If they develop cosmology at all, they'll come up with a very different picture. A small, static universe, eternal and unchanging. They'll be wrong, but they'll have no way to know it. The evidence will have slipped beyond the horizon. The scientists who realized this weren't looking for something depressing, they were just following the math. In the late 1990s, after the discovery of dark energy and the acceleration of the universe, cosmologists started calculating what that meant for the long-term future. They mapped out the fate of galaxies, the evolution of stars, the eventual heat death of the universe. And in the process, they discovered this odd consequence. The universe is not just expanding, it's erasing its own history. The very thing that makes it interesting, the story of its origin and evolution, is being written in disappearing ink. We're fortunate to live in an era when the ink is still visible, when the cosmic microwave background is still bright enough to see, when distant galaxies are still within reach of our telescopes. But even now, we're missing pieces. There are galaxies beyond our current horizon that we'll never see, that have always been too far for their light to reach us. And because the expansion is accelerating, that horizon isn't expanding, it's contracting. The edge of the observable universe isn't a fixed distance. It's a moving target, and it's moving toward us. New galaxies aren't coming into view. Old ones are disappearing from it. Every moment, the universe we can observe is getting slightly smaller in terms of what's causally connected to us. We're not just isolated in space. We're becoming more isolated over time. This affects more than just astronomy. It touches on something philosophical, something existential. We like to think of knowledge as cumulative, that each generation builds on the discoveries of the last, that the arc of science bends toward understanding. But what if some knowledge has an expiration date? What if there are questions we can answer now that will become unanswerable in the future? Not because we've lost the ability to think, but because the evidence has vanished. The cosmic microwave background will eventually cool and fade until it's indistinguishable from the background noise of space. The distant galaxies will redshift into invisibility, and the universe will keep its secrets not because it's fundamentally unknowable, but because it's moving the goalposts faster than we can reach them. There's a project underway, a kind of cosmic time capsule, though it's not an official mission. It's more of an idea that floats around in the cosmology community. The thought is this: if we know that certain observations will become impossible in the future, should we preserve them? Should we encode everything we've learned about the early universe, the Big Bang, the cosmic web, the expansion history, into some durable format that could survive for trillions of years? It's not practical, not yet. We don't have materials that last that long, don't have a way to ensure any civilization in the distant future would find it or be able to read it. But the impulse is understandable. A desire to leave a message in a bottle for whoever comes after. A note that says, the universe was bigger once, stranger once, and we saw it while we could. You're lying in the narrow slice of time when the universe is still knowable, when its history is still written in light we can catch. Billions of years in the past, the universe was too young, too hot, too opaque to observe itself. Trillions of years in the future, it will be too old, too cold, too empty. But right now, tonight, in this brief era between fire and ice, there's enough light to see by, enough structure to study, enough evidence to piece together the story. We're living in the golden age of cosmology, even if we don't always realize it. The James Webb Space Telescope is looking deeper into the past than ever before. The Planck satellite mapped the cosmic microwave background with exquisite precision. Ground-based observatories are surveying millions of galaxies, tracing the cosmic web, measuring the acceleration. We're gathering data while we still can, answering questions before they become unanswerable. And that brings us back to you, lying in your bed, staring at the ceiling or into the dark. You're not separate from this story. You're part of the narrow window, part of the brief moment when the universe can look at itself and understand what it sees. In some real sense, you're the universe waking up, becoming aware, asking questions about its own size and origin and fate. That awareness won't last forever. The stars will burn out, the galaxies will drift apart, the cosmic microwave background will fade, and eventually there will be nothing left but cold, dark, isolated pockets of matter drifting through an ever-expanding void. But that's not now. Now, there's still light. Now, there's still time. Now, you're still here, still listening, still part of the living universe that hasn't yet forgotten where it came from. Rest in that. It's enough. You're still here, still breathing in the dark. And now we're going to step into one of the strangest territories in all of cosmology. The possibility that the universe isn't just big, but infinite. Not so large we'll never see the end. Infinite. But actually, truly, mathematically infinite. No edges, no boundaries, no matter how far you travel. And if that's true, if space goes on forever, then the implications become bizarre in ways that twist your intuition into knots. Because in an infinite universe, with infinite space and infinite matter, everything that can happen doesn't just happen once. It happens infinitely many times, including you. Let's walk through this carefully. We know the observable universe is finite, 93 billion light-years across, bounded by the speed of light and the age of time. But that's just what we can see, the bubble carved out by our particular position in space and the particular moment in cosmic history we happen to occupy. The question is, does the universe stop at the edge of our bubble, or does it keep going? The measurements from the cosmic microwave background suggest space is flat, and in most models, a flat universe that goes on in all directions doesn't curve back on itself. It just continues, infinitely. There's no edge to run into, no wall marking the end. Just more space, more galaxies, more stars, forever. If that's the case, and if the universe is not just infinite but also roughly uniform, meaning the same kinds of structures appear everywhere, the same laws of physics apply, the same distribution of matter repeats across vast distances, then something very strange follows. There are only so many ways you can arrange particles in a given volume of space. It's an incomprehensibly large number, but it's still finite. A region the size of the observable universe contains about 10 to the 80th atoms. Each of those atoms can be in different positions, different states, different configurations. The total number of possible arrangements is huge, maybe 10 to the 10 to the 120. But it's not infinite. And if space is infinite, then every possible arrangement must repeat somewhere out there, infinitely many times. That means there's another version of you right now, lying in a bed in a room that looks identical to yours, on a planet identical to Earth, in a galaxy identical to the Milky Way, listening to these exact words. Not nearby, almost certainly not within the observable universe, but somewhere out there beyond the horizon, beyond the reach of light. How far? The estimates vary, but if you assume the universe is infinite and uniform, you'd expect to find an identical copy of the observable universe at a distance of about 10 to the 10 to the 118 meters. That's a number so large it doesn't fit in your head. It's not just bigger than the observable universe, it's bigger than any distance you can visualize. But in an infinite universe, even that incomprehensible distance is crossed infinitely many times. And it doesn't stop there. If every possible arrangement happens somewhere, then there are versions of you where things went slightly differently. A version where you chose a different book to read tonight. A version where you're already asleep. A version where you never clicked on this video at all. There are versions where history unfolded differently, where Rome never fell, where dinosaurs never went extinct, where Earth never formed. Every possibility that doesn't violate the laws of physics gets realized somewhere, scattered across the infinite expanse like different rooms in an endlessly sprawling mansion. You're not unique. You're one instance of a pattern that repeats, varies, repeats again, forever. This is called the infinite duplicate problem, and it makes some physicists deeply uncomfortable. Not because it's illogical, it follows naturally from the assumptions, but because it feels meaningless. If there are infinite copies of you making every possible choice, then what does choice even mean? If every version of history is playing out somewhere, then what's special about this one, the one you're living right now? Some philosophers argue that it doesn't matter. You're still you. Your experiences are still real. The fact that there might be other yous doesn't diminish the reality of this moment, here, now, in this room, listening to this voice. But it's hard to shake the vertigo that comes with the idea. There's no way to test this directly. We can't travel beyond the observable universe to check if there's another Earth out there. We can't send signals faster than light to compare notes with our duplicates. The infinity, if it exists, is forever beyond our reach. But we can test whether the universe is infinite by refining our measurements of its curvature. If space is even slightly positively curved, then it's finite, wrapping back on itself like the surface of a sphere. If it's negatively curved, it could still be infinite, like a saddle that extends forever. And if it's exactly flat, as the data currently suggests, then infinity is the most natural conclusion. Future missions, better satellites, more sensitive detectors, might narrow the error bars enough to rule out certain possibilities. But we might never know for sure. The scientists working on this aren't sitting in existential dread. They're running simulations, analyzing data, refining cosmological models. The Planck satellite measured the curvature of space to within 0.4% of flat. The next generation of cosmic microwave background experiments, planned for the 2030s, might push that precision even further. There are also projects trying to map the large-scale structure of the universe in more detail, looking for patterns or anomalies that might hint at finite topology, signs that space loops back on itself in unexpected ways. If we found evidence of that, it would mean the universe is large but not infinite, and the duplicate problem would vanish. But so far, the data points toward flatness, and flatness points toward infinity. Here's another angle on it. Even if the universe is finite, it could be so large that it might as well be infinite for all practical purposes. Imagine a universe that's 1 trillion times bigger than the observable universe, large enough that no signal from one side could ever reach the other, large enough that causally disconnected regions vastly outnumber connected ones. In that case, whether it's technically infinite or just absurdly huge doesn't change much. You'd still be isolated in your pocket of space, still unable to visit or communicate with the vast majority of what exists. The difference between really big and infinite becomes philosophical rather than physical. And there's a third possibility, stranger still. What if the universe is infinite in some directions but not others? What if space has a complicated topology, looping in some dimensions while extending forever in others? Mathematicians have studied these shapes, three-dimensional manifolds with names like the Poincaré dodecahedral space or the three torus. They're consistent with the laws of general relativity, and some of them would produce subtle signatures in the cosmic microwave background, repeating patterns, correlations at specific angular scales. Researchers have searched for those signatures and found nothing conclusive. But the absence of evidence isn't evidence of absence. It just means that if the universe has weird topology, it's either very large or very subtle. You don't need to decide tonight whether the universe is infinite. You don't need to imagine your duplicates scattered across eternity. Just hold the possibility lightly, the way you'd hold a strange stone you found on a beach, interesting, unsettling, but not something you have to carry forever. The universe might be infinite, it might not. Either way, you're here, in this particular arrangement of atoms, in this particular moment of time, listening to this particular voice in the dark. That's real. That's undeniable. And whether or not there are infinite other versions of you out there, this version, this one, right here, right now, is the only one you'll ever experience. So rest. Let the infinity wash over you like a wave that never quite reaches the shore. You're safe here, you're singular here, even if the cosmos isn't. That's enough. You're deep into the night now, deep into the journey, and the questions are starting to bend inward. We've looked out at the farthest edges of space, traced the expansion back to its beginning, considered the possibility of infinity. But now we need to ask something quieter, something that sits closer to the bone. In a universe this big, this old, this indifferent to human scales, what does it mean that you're here at all? Not in some abstract philosophical sense, but literally here. A temporary arrangement of atoms that somehow learned to ask questions about the arrangement. You're made of matter that's been recycling through stars for billions of years, and you'll return to that cycle soon enough. So what are you really, in the context of all this immensity? Let's start with the atoms in your body. Every single one of them, except for hydrogen, which is primordial, left over from the Big Bang, was forged inside a star. The carbon in your cells, the oxygen you're breathing right now, the calcium in your bones, the iron in your blood. None of that existed in the early universe. It was created later, over billions of years, through nuclear fusion in the cores of stars and the violent explosions that ended their lives. Stars are element factories. They fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table, building heavier and heavier elements until they reach iron. And then, if the star is massive enough, it dies in a supernova, a blast so powerful it creates the even heavier elements, gold, silver, uranium, and scatters them into space. That material drifts through the galaxy as dust and gas, eventually collapsing under gravity to form new stars, new planets, new possibilities. Earth formed about 4.5 billion years ago from a cloud of debris orbiting a young sun, and that debris carried the remnants of earlier stellar generations. The ground you're standing on, the air you're breathing, the body you're living in, it's all stardust, quite literally. You're not separate from the cosmos. You're a local concentration of it, a pattern the universe is making with recycled material. In a very real sense, you're the universe looking at itself, a temporary eddy in the flow of matter and energy that's been swirling for 13.8 billion years. But here's the unsettling part. You won't last. Not you personally, not humanity, not Earth, not even the stars. Everything has a lifespan in this universe, and the scales are brutal. The sun will burn for another 5 billion years, then swell into a red giant, consuming Mercury and Venus, possibly Earth. Long before that, in about 1 billion years, the sun will heat up enough that Earth's oceans will evaporate, and life as we know it will become impossible. Humanity, if it still exists, will have to leave or die. And even if we escape, even if we spread across the galaxy, colonize 1,000 worlds, build civilizations that last for millions of years, eventually, the stars themselves will run out of fuel. Star formation will slow and stop as the universe uses up its hydrogen. The last stars will flicker out in about 100 trillion years, a timescale so long it makes the current age of the universe look like a brief flicker. After that, the universe will be dark, filled with cold remnants, white dwarfs, neutron stars, black holes, and clouds of inert gas drifting through the void, and even those remnants won't last forever. Black holes will evaporate through Hawking radiation over timescales of 10 to the 100 years. Protons themselves might decay, given enough time, dissolving into lighter particles and radiation. The universe will reach a state called heat death, maximum entropy. No energy gradients left to drive any process, no structure, no complexity, no life. Just a thin, cold, empty expanse, approaching absolute zero, silent and still. This is the timeline cosmologists have mapped out based on our current understanding of physics. It's not speculation, it's extrapolation, following the laws we know to their logical conclusions. Researchers at places like Caltech, Oxford, and the Max Planck Institute have run the calculations, modeled the far future, written papers with titles like The 5 Ages of the Universe and Time Without End. They describe a cosmos that begins in fire and ends in ice, where everything interesting, stars, galaxies, life, thought, happens in a narrow window near the beginning. We're living in that window now. The universe is young. Stars are still being born. Galaxies are still colliding and merging. There's still light, still warmth, still the possibility of complexity. But it won't last. That sounds bleak, and maybe it is. But there's another way to look at it. The fact that you exist at all, as in this brief moment between the Big Bang and the heat death, is wildly improbable. The odds of any particular arrangement of atoms coming together to form a living, thinking being are astronomically small, and yet here you are, not because the universe intended it, there's no evidence the universe has intentions, but because the conditions were right, the chemistry worked out. Evolution stumbled forward through trial and error for billions of years, and eventually there was you. Temporary, yes. Fragile, yes. But real and aware, and capable of understanding, at least partially, the vast context you're embedded in. Some scientists find comfort in that perspective. Carl Sagan used to talk about it, the idea that we're a way for the cosmos to know itself. The universe spent billions of years unconscious, just matter following physical laws, and then, on at least one small planet orbiting an ordinary star, it woke up. It became aware. It started asking questions, and that's not nothing, that's remarkable. You're not an accident in the sense of being meaningless. You're a natural consequence of the laws of physics playing out over deep time. Stars had to form and die to create the elements. Planets had to condense from dust. Chemistry had to complexify. Life had to emerge and evolve. And all of that led, step by improbable step, to you lying in the dark, listening to a voice talk about the size of everything. But not all scientists are comforted by that. Some find the scales oppressive, the realization that humanity's entire history, from the first stone tools to the launch of spacecraft, is a blip in cosmic time, less than a millisecond if you compress the age of the universe into a single day. Everything we've built, everything we've learned, everyone who's ever lived, it all fits into the tiniest sliver of the timeline, and it will all be forgotten eventually. Not just culturally forgotten, but physically erased. The heat death of the universe doesn't care about Shakespeare or the pyramids or the moon landing. It doesn't preserve anything. In the end, there's no record, no archive, no memory, just cold, empty space. There's a term for this feeling, cosmic pessimism, or sometimes existential vertigo. It's what happens when you zoom out too far, when you confront the sheer indifference of the universe to human concerns. The philosopher Blaise Pascal wrote about it in the 17th century, long before modern cosmology. The eternal silence of these infinite spaces frightens me. He was talking about the night sky, the realization that the stars were distant and uncaring, and he didn't even know about the expansion, the heat death, the eventual evaporation of black holes. We know more now, and the picture is even more stark. The universe is vast, old, and cold. It will outlast us by an incomprehensible margin, and it won't notice when we're gone. But here's the thing, none of that changes the fact that you're here now. The heat death is trillions of years away. The sun won't die for billions. You have this moment, this breath, this quiet hour in the dark, and maybe that's enough. Maybe meaning doesn't need to be eternal to be real. Maybe the fact that you're temporary doesn't make your thoughts less valuable, your experiences less vivid, your connections less significant. You're a pattern in the flow, yes, but patterns can be beautiful even when they don't last. A wave on the ocean is still a wave, even though it dissolves back into the water after a few seconds. It was real while it existed. So are you. You don't have to resolve the tension tonight. You don't have to decide whether the universe's indifference is terrifying or liberating, whether your smallness is crushing or clarifying. Just rest in the knowledge that you're part of something unimaginably large, that you're made of ancient material, that you're a brief flicker of awareness in a cosmos that's mostly dark and silent. And for now, that flicker is enough. You're still here, still breathing, still listening. The universe is vast, yes, but so is the fact that you're aware of it. Hold both of those things gently, let them coexist, and rest. You're near the end now, near the place where the questions stop having answers and start dissolving into something else. Acceptance, maybe, or wonder, or just exhaustion. We've traveled from the observable universe to infinity, from the Big Bang to the heat death, from the constants that hold reality together to the realization that none of it lasts. But there's one more thing we need to talk about, one more piece of the puzzle that sits at the intersection of everything we've covered. The fact that we don't actually know what most of the universe is made of. We've mentioned dark matter and dark energy in passing, but now we need to sit with that ignorance for a moment. Really feel the weight of it. Because when we ask, how big is the universe, we're also asking, what is the universe? And the honest answer is, we don't know. Let's revisit the accounting. Zit. Ordinary matter, the stuff that makes up stars, planets, gas clouds, everything we can see and touch, accounts for about 5% of the universe's total energy content. 5%. That's it. The rest is split between dark matter at 27% at Tor and dark energy at 68%. We've never directly detected either one. We know they're there because of their effects. Dark matter through its gravitational pull on galaxies, dark energy through the acceleration of the expansion, but we don't know what they are. We've given them names, built models around them, written thousands of papers exploring their properties, but we haven't found them. We're living in a universe where 95% of the content is invisible, untouchable, mysterious. Dark matter was inferred first, back in the 1930s, when an astronomer named Fritz Zwicky was studying the Coma cluster, a group of galaxies bound together by gravity. He measured how fast the galaxies were moving, calculated how much mass would be needed to hold them together, and found a discrepancy. The visible matter, stars, gas, dust, wasn't nearly enough. The galaxies were moving too fast. They should have flown apart. Something else had to be there, providing extra gravity, something that didn't shine. Zwicky called it dunkel Materie, dark matter. Most astronomers ignored him. The idea was too strange, too unsettling. But decades later, in the 1970s, Vera Rubin found the same problem in individual galaxies. Stars at the edges of spiral galaxies were orbiting too fast, moving as if there was far more mass than the visible stars and gas could account for. The only explanation was a halo of invisible matter surrounding each galaxy, providing the gravitational scaffolding. Since then, dark matter has become central to our understanding of cosmic structure. It's the framework that galaxies form on, the gravitational glue that holds clusters together, the reason the cosmic web looks the way it does. Simulations of the universe's evolution only match observations if you include dark matter. Without it, galaxies don't form in the right places. Clusters don't hold together. The large-scale structure falls apart. So we know it's there. We just don't know what it is. Candidates include WIMPs, weakly interacting massive particles, hypothetical particles that only interact through gravity and the weak nuclear force, or axions, ultra-light particles predicted by certain extensions of the Standard Model, or primordial black holes formed in the early universe before stars existed, or something else entirely, something we haven't thought of yet. Physicists have built detectors to search for dark matter particles, burying them deep underground to shield them from cosmic rays. Experiments like Xenon in Italy, Lux Zeppelin in South Dakota, and Pandax in China use tanks of liquid xenon, waiting for a dark matter particle to collide with a xenon nucleus and produce a faint flash of light. They've been running for years. They've ruled out large swaths of parameter space, eliminated many possible candidates, but they haven't found anything yet. Either dark matter particles are rarer or more elusive than we thought, or we're looking in the wrong place, or the whole framework is mistaken and we need a different explanation. Some physicists have proposed modifications to gravity, theories where gravity behaves differently on large scales, eliminating the need for dark matter altogether. But those theories have their own problems, and most cosmologists still favor dark matter. Dark energy is even stranger. It wasn't predicted. It was discovered by accident, the same way Penzias and Wilson stumbled onto the cosmic microwave background. In 1998, two teams measuring distant supernovae found that the expansion of the universe was accelerating, and the only way to explain that was to invoke some kind of energy filling space itself, pushing everything apart. We call it dark energy, because we don't know what else to call it. It doesn't clump like matter. It doesn't dilute as the universe expands. It just sits there, a constant energy density built into the fabric of space. The simplest explanation is Einstein's cosmological constant, the same term he added to his equations and later regretted. But if that's what it is, if dark energy is just the vacuum energy of space itself, then the measured value is absurdly small compared to what quantum field theory predicts. The prediction is off by a factor of 10 to the 120. That's not a small error. That's the worst prediction in the history of physics. No one knows how to fix it. Some theorists think there's a deeper principle that sets the vacuum energy to nearly zero. Some symmetry or cancellation we haven't discovered. Others think dark energy isn't constant at all. It's a field that evolves over time, something called quintessence, named after the fifth element of ancient philosophy. If that's true, then dark energy might get stronger or weaker as the universe ages, and the ultimate fate of the cosmos might be different than we think. There are missions planned to measure this, space telescopes that will map millions of galaxies, track the expansion history with exquisite precision, search for hints that dark energy is changing. The Euclid telescope, launched by ESA in 2023, is doing this now. NASA's Nancy Grace Roman Space Telescope, launching soon, will join it. They'll measure the positions and redshifts of galaxies, trace how structure has grown over time, and look for deviations from the cosmological constant model. But there's a possibility that haunts some physicists late at night. What if we're not smart enough to figure this out? What if dark matter and dark energy are real, but the explanation requires physics so far beyond our current understanding that we'll never find it, or at least not for centuries? Humans have been doing science for a few hundred years. We've made extraordinary progress, but we're still limited by our biology, our technology, our perspective. We're apes with telescopes, clever apes, but apes nonetheless. There's no guarantee the universe is comprehensible to us. There's no law that says the answers have to be within reach. We might be staring at the evidence for something we're incapable of understanding, like showing a calculus textbook to a mouse. That's a humbling thought, and it's one that serious scientists take seriously. Not as an excuse to stop trying. Everyone's still building detectors, still analyzing data, still searching for patterns, but as a reminder that confidence should be tempered with humility. The universe has surprised us before. It was bigger than we thought, older than we thought, stranger than we thought. It expanded when we expected it to contract, accelerated when we expected it to slow. It's made of things we can't see, governed by constants we can't explain, possibly infinite in extent. Every time we think we've got it figured out, it reveals another layer of complexity. And maybe that's just the way it is. Maybe the universe is always one step ahead, always holding something back. You're lying in a universe where 95% of the content is invisible. You're surrounded by dark matter right now. It's passing through your body, through the earth, barely interacting with anything. Dark energy is embedded in the space between your atoms, pushing the distant galaxies farther away. And you can't feel any of it. You can't see it, can't touch it, can't measure it directly. You only know it's there because scientists spent decades looking at the sky, measuring tiny distortions and unexpected motions, and realized that the visible universe is just the tip of an enormous iceberg. The rest is hidden, maybe forever. And maybe that's okay. Maybe not knowing is part of the experience. We've mapped the observable universe, traced its history, measured its expansion, catalogued its structures. We've done more in the last century than in all of human history before that, but the universe is under no obligation to make itself fully transparent to us. It keeps its secrets, It holds back, and in that holding back, there's a kind of grace, a reminder that we're not the center, not the pinnacle, not the final word. We're participants in something much larger, something that started long before us and will continue long after. We get to see a piece of it, understand a fraction, marvel at the rest. That's the deal, and it's not a bad deal, all things considered. So rest now. Let the dark matter pass through you unnoticed. Let the dark energy push the galaxies away. You don't have to solve the mystery tonight. You don't have to know what 95% of the universe is made of. Just know that you're here, in the 5% ilaos, made of atoms that shine and bond and think. That's rare. That's precious. And for now, that's enough. After traveling through distances that stretch intuition and futures that outlast memory, something subtle begins to change. The universe no longer feels like a question that needs answering. It starts to feel like a condition you are already inside. Size stops being a challenge to overcome and becomes a background presence, steady and unthreatening. At first, vastness feels like pressure. Numbers pile up. Light years blur together. The mind tries to hold everything at once and fails, but after enough exposure, the effort dissolves. The universe does not demand comprehension to function. It allows you to stop reaching without consequence. This is often how astronomers describe their relationship with scale after years of work. Early fascination is intense, almost overwhelming. Later, something calmer takes its place. The universe remains enormous, but it no longer feels hostile to understanding. It feels familiar in its refusal to be fully known. Familiar does not mean small, it means predictable in its behavior. Gravity behaves reliably. Expansion follows measurable rules. Light travels as expected. Even mystery has structure. The universe is not chaotic at large scales. It is consistent, even when it is vast. This consistency is what makes the cosmos feel inhabitable rather than alien. Life does not exist despite the universe's size. It exists because the universe is stable enough, old enough, and large enough to allow complexity to emerge slowly, without interruption. Every atom in your body has followed paths shaped by cosmic scale. Elements forged in ancient stars dispersed across galaxies, condensed into planets, and eventually participated in biology. The same expansion that carries galaxies apart also created the space where this long chain of events could unfold without collision. In this sense, size becomes enabling rather than isolating. A smaller universe might be denser, more violent, less forgiving. This one has room to breathe. It allows processes to finish. It allows mistakes without immediate collapse. Late at night, this perspective softens the edges of thought. The universe does not feel like something towering above you. It feels like something surrounding you evenly, without direction or hierarchy. There is no up or down in cosmic size, only inclusion. Expansion no longer feels like separation alone. It feels like spacing, giving structure room to exist without interference. Galaxies drift apart, but stars remain bound. Systems persist locally, even as the whole grows larger. This layered stability is key. The universe is not one single scale repeated endlessly. It is many scales coexisting without conflict. The human scale fits inside planetary scale, which fits inside stellar scale, which fits inside galactic scale. None invalidate the others. You are not misplaced in this structure. You are scaled correctly for where you exist. Your body responds to local gravity, local time, local chemistry. The universe does not ask you to function at cosmic scale to belong within it. When the mind finally accepts this, vastness stops feeling like erasure. It feels like permission. There is no need to rush understanding, no need to compress infinity into clarity. You are allowed to exist comfortably inside partial knowledge. Scientists live with this partial knowledge every day. They publish results knowing they are incomplete. They refine models knowing they will be revised. The universe remains steady while explanation evolves around it. This steadiness is what allows rest. Reality does not wobble when questions go unanswered. It does not destabilize when attention fades. Size does not increase pressure, it absorbs it. The question, how big is the universe, really, now feels less urgent than it did at the start. Not because it has been answered, but because it no longer needs to be. The universe can be large without being threatening, and here, within this immense structure, there is a quiet sense of fit, not importance, not centrality, just placement. You exist where you are supposed to exist, supported by the same laws that govern galaxies. The universe is vast, expanding, and ultimately unreachable in totality. And yet, it is calm enough, stable enough, and coherent enough to be lived inside, even briefly, even quietly, even while resting. As this part comes to a close, nothing needs to resolve further. The scales have done their work. The pressure has eased. What remains is a sense that size, once intimidating, has become simply the space in which rest is possible.